This is part two of week 9. Just want to talk about pump checks. Um, the trick here is to make sure and see if the pump is actually working. In order to do this, you must see if the water is being circulated. You can adjust the aquastat that turns the pump on. Different scenarios or different boilers have. Some of them wait for the water to heat up to turn the pump on. Some of them turn the pump on as soon as there's a call for heat. They're all a little different. But there's sometimes there's a flow switch, and you'll see a flow switch sitting in the bottom of this PowerPoint here. And a flow switch is sensing that the pump is actually pumping the water around. In different scenarios, taking the pump out of the system can prove the flow switch is working properly and the burner should not come on. So in almost all scenarios, the burner should only come on if the pump is running. Most high efficiency boilers have built-in flow valves that check that the pump is running, and they will not allow the boiler to fire. If it did, you basically just would turn all that water to steam. Let's take a look at a diagram here. And this is just one of many different ways that you could wire in a system. Let's just take a look at what might happen here. You guys will recognize, obviously, a transformer in the middle here. We got a circuit breaker and a service switch. There's your pump at the top. It's called system pump. And there's a relay switch on the side of it. Underneath that, it's a little different. You'll see a thermostat. And a thermostat on a boiler not are always identified as R and C, although this one is with an R and a C. But sometimes identified as T and T, which means thermostat and thermostat. Obviously, we don't need other letters because you can't put air conditioning on a boiler. So you'll have a thermostat that closes, and that thermostat will power what's called a zone valve. And that zone valve is a 24-volt valve. It's a load, and what it does, it opens and allows the water to start flowing, or if it could flow. When it fully opens, it closes a switch called the end valve, zone valve end switch. And at that point, the R continues through, and then it will power this primary relay. That's a coil. That will then close the system pump right there, PRA, and the system pump closes. And these two aquastats are normally closed. Right now they're shown in the open position. I have no idea why. But this boiler operating unit would be at 180 degrees. The boiler high limit is operating at 200 degrees, 20 degrees higher. So what you get is this. R comes through, the end valve, zone valve end switch is closed, goes through the two open switches and powers the gas valve. So now the water is being heating up. The pump is already running. What will happen here is as soon as we get to 180 degrees, this boiler operating aquastat opens. The high limit stays closed because it's not at 200 degrees, and it'll cut the power to the gas valve. This boiler operating thermostat aquastat will open and close as the heat gets dissipated from the water. Meanwhile, the pump runs all the time, the thermostat's still calling for heat, and the zone valve is open. So this allows the water to go through the system. Let's just take a look at analyzing and identifying control malfunctions. We're going to talk about boilers. They're very prone to carboning, which means that if the boiler doesn't, burners aren't set up properly, that they will create a lot of carbon and carbon monoxide. We'll talk in a couple minutes here about some TSSA mandates. I'll probably do it on a completely different video here. But what we're going to look at here is boiler problems. So carboning is usually caused by flame impingement or such as air adjustment or overfired. Carboning is a very black, fine dust. It's not really a dust, it's a chemical, black carbon. You'll see it on candles, that kind of stuff, right? When it happens on a boiler, it is a mess. And you have to completely disassemble the boiler to try and get rid of this carboning. You'll want to get rid of all of it. It does a couple things. It insulates the boiler so that you get no heat transfer. So the more carbon you make, the longer the boiler runs, the more carbon you make. So it's a really detrimental thing to a boiler. So that's why boilers, you want to make sure that they're nice and clean and that you have a good heat transfer. Condensation. Condensation is where we're cooling the flue gases off too much. And you might do this if you have what's called a cold boiler, or too much water flow through the boiler, or there's a couple things there. Typically, that's already done in the design of the boiler. It's not usually something that you can make changes to. Corrosion is caused by air in the system. There's two ways that the air can, in the system, two ways air can enter. They can enter through obviously a leak in the system, or they can enter through one of the valves that lets the air out. Air in the system is usually, if you bring in too much new water, there's air in the water, and that can congregate and cause a problem. Another thing that the boiler happens in the boiler is what's called underfiring or overfiring. Overfiring is much more critical and could cause CO and other issues. Underfiring will get you that condensation situation. So a boiler, you want to make sure that it's fired within about 10% of its full input. So if it's 100,000 BTU, you want to fire it between 90 and 100,000 BTU. You do not want to fire it at 110 BTU or 105 or 102. Always underfire a boiler, right? Just a little bit. Mechanical problems, insufficient heat output, typically caused by insufficient or no flow in the system or incorrect temperature settings. So there's different things you can run into for why that is. Those are mechanical problems. Noise in the system can be caused by the following: air in the system, zone valves installed backwards, they slam shut. That's usually a initial installation thing. It's not something that you run into. It just does it on its own. Pumps that are undersized and run at excessive RPM, that will cause you. Remember, any kind of noise on a boiler system reverberates through the entire system. It's kind of like pounding on ductwork, right? You'll hear it throughout the entire house. Poorly secured piping supports permit noise through vibration, and inadequate expansion and contraction clearances between piping and building structure. If you screw the copper for the water that goes through it directly to a joist, that copper is going to want to expand and contract based on if it's hot water or cold water going through the piping, and will make creaking noises. I had them in my old house. There was no way I could get to them. I just had to live with it. But on a new installation, that's something you'll want to take a good look at. Pump cavitation is a formation of bubbles in a liquid by pressure variance or heating or vibration. Pump cavitation sounds like gurgling or popping sounds. And it's where the outlet of the pump is creating air bubbles. So we can reduce this pump cavitation, where we're producing these bubbles or this noise, by locating the expansion tank as close to the boiler as possible, installing the pump as low as possible to increase the static pressure at the inlet of the pump. So remember, all the water above the pump pushes down onto the boiler and the pump. The pipe leading to the pump must be straight, or at least 10 sizes longer than the pump size. So you can't have an elbow and then the pump. You would, if the pipe is 1 inch, you'll want it 10 inches from that elbow. So without drawing you a picture here, which is something that's making me difficult here, you'll just want to make sure the pipe leading to the pump must be straight, or at least 10 sizes longer than the pipe's size. So if it's 2-inch pipe, you want 20 inches of straight pipe in front of it. Okay, so something easily. And then installing air removal devices would be another way that we can get rid of what we call pump cavitation. So again, pump cavitation is the pump creating kind of like water bubbles by trying to suck in some water or pump some water around that doesn't have a good flow of water. So let's see, I'm going to stop this video. I'll do a last one here on something called the TSSA mandate. So I'll be back in a minute.